So today we're going to review some things. And I know this is going to seem, I mean, like you guys have done this a lot, and so this should go pretty quickly. But there are a few things I want to talk about and show you that I think will help you not just remember this stuff, but conceptualize it in a way where it'll stick better. Okay, well, you'll kind of understand why these patterns exist that we're going to talk about with lines. So we're going to look at linear relations. When points on a graph lie along a straight line, we call that a linear relation, right? The equation that we would attach to that would be a linear equation. We have different ways of writing those. Okay, we could write something like here's one example of a way that we could write a line in the form x plus y equals 8. The one you're most familiar with is probably point slope form, and we'll get to that. But there are other forms that we use, and one of those is called standard form. Standard form is one that, why is it a big deal? Because when we deal with systems of linear equations, we always want to write the linear equations in standard form when we're solving systems. And I'm going to show you guys some kind of higher level things that we can do with solving big linear systems, like even huge linear systems, using technology. So I'll show you some ways that we can accomplish that, because that's a really powerful tool. But right up front, the reason I bring that up is because this tool relies on writing all of the linear equations in the system. They have to be written in standard form. Okay. All right. So what is standard form? So standard form is just this. Standard form is the form ax plus by equals c, where capital A, capital B, and capital C are the coefficients, right? A is the coefficient of x, B is the coefficient of y, and C is the constant. Now, there are some rules that go with this here. And some of these rules aren't always enforced, but it's a good idea to get used to them. One of them is that A has to be positive, has to be greater than or equal to 1, okay? Okay, so that doesn't always, like I was trying to find questions. This Math Excel, gosh, it's difficult to find questions for you guys for an advanced class like this sometimes. And I was looking through different textbooks trying to find some questions we could use to practice writing in standard form. And a lot of these textbooks, I noticed, I had to go in and change the code, because they don't even, in these textbooks, they say A could be negative. And so you do see that sometimes. If you change from one textbook to another, sometimes that's a rule that's enforced, and sometimes it's not. It is a good idea for A to be positive, though. Okay, it doesn't always have to be that way. I'll say right now, it doesn't have to be that way, and we may not even enforce that rule once we start solving linear systems. Okay, but for now, just get used to the idea that sometimes we enforce that rule. And all it means, if A is negative, is I multiply both sides of the equation by -1 and change the signs, right, to make A positive. Okay, the other one, and this is a more important rule, is that the greatest common factor of A, B, and C is 1. Okay, so A, B, and C, and the other, and even more important, I skipped over this one. A, B, and C have to be integers. They can't be fractions. Okay, they have to be integers for us to be able to write this, in standard form. Okay. Now, the greatest common factor of A, B, and C is 1. So we wouldn't want to get something like 4 and 8 and 12 there, because I could just divide both sides of the equation by 4 and make those coefficients smaller. So this is a simple way of saying we want to make A, B, and C as small as possible and yet have them be integers. Okay. So what would we have to do here to number 1, if we want to put it's almost in standard form? What's the only thing I have to do to put this into standard form? What do you think? Sarah House, what do I have to do here to put this into standard form?
You have to divide by -1.
Yeah, either multiply or divide by -1. So I'm just changing all the signs, aren't I? So that's going to become a 5x. That's going to become a -6y. That's going to become a +12. And that's it. No big deal, right? What about here? Let's look at one quick example. On this one, I'd have to move the 2x over to the other side, right? I'd have to subtract 2x from both sides, and then I'd have to change the signs, either multiply or divide by -1. So I end up with a +2x, a -y, and a +9. No big deal. Okay, I mean, over here, what's the one thing I have to do? You know, I got to add the 24. Let's look at a little harder one. What about something like that, number 5? What would I do there? What would I do there? What do you think, Rebecca? I got to put that into standard form.
Wouldn't you multiply them both by 12?
Yes, good. We want to clear the fractions, don't we? Because we need integer coefficients. So there's my first step, is I'm going to multiply, I'm going to distribute through both sides 12. And so we could do our little trick, couldn't we? We end up with 12 over 4 reduces to 3, which we multiply by the numerator. So 3 times 3 is 9x. 12 over 3 reduces to 4, which I multiply by the numerator. So I get a minus 4y, and then 12 times 1 equals 12. And then I'm done, aren't I? Okay, you guys get the idea, right? And then same kind of thing here, right? I could just multiply both sides through by 6, and I end up with x equals 6y minus 12, and then I got to subtract the 6y from both sides. So I get x minus 6y equals negative 12. Okay, that's probably enough for us, right? That's standard form. Okay, slope-intercept form. This is the one you're most familiar with. What's Rebecca? What's other Rebecca? Rebecca Bertram. What's slope-intercept form? You probably remember that. Good. Y equals mx plus b. Or another way of saying it is we could use function notation and say f of x equals mx plus b. Okay. Where m is what? What's m stand for?
Well,
Okay, good. Slope. And remember what b stands for?
initial value.
Initial value. Okay. A lot of times when we're doing, right, if we're doing like applications, it would be the start value or the initial value. If we're looking just in terms of graphing it, right, in terms of what does it mean in terms of a graph, it would just be the y-intercept, wouldn't it? Okay. And so let's just briefly review what this stuff means. Now, I want you to think about something, though, before we go any further. When we're writing lines in these various forms, like we could write this in slope-intercept form, for example, the m and the b are the parameters that we use to dial in the line. Okay, so imagine that those are values, and there's some interactive tools that we'll use where you'll get a chance to do this a little bit. But by tweaking the values of m and b, we're creating any conceivable line, aren't we? Right? And in fact, here, I'll tell you what, I'm going to, just because this is not so much for what it shows you, but because I want you to get used to Desmos, let's just practice this a little bit. Let's show you a couple tools on Desmos. Desmos is really fun to use. I want you guys to become experts with Desmos. So if we pull up the Desmos graphing, and let's just make the equation of a line. Okay, so let's do something like y equals mx plus b. And notice it asked me if I want to add sliders for m and b. Yeah, I do. So I'm going to add these sliders. Now look what this does. When I add these sliders, it allows me to take the values of m and change them. And look what that does, right? It just changes obviously that just changes the slope of the line. And by changing the value of b, it changes the y-intercept of the line, okay? And so I can just type in any value I want to. I don't have to slide it. I could say m equals 3/2, and I could let b equal 8 if I want to, right? And I can type those things in. That's a really handy thing to do in Desmos. You can almost do some rudimentary programming in Desmos when you start to get used to it. It's really a good tool, and I actually think it is a good tool for getting you thinking about things in the way that's going to be helpful when you actually do some coding later on in life, right? Okay, so my point being there, though, that with those parameters, we could create any possible line in the infinite xy plane, okay? So a line only requires two pieces of information for us to specify any possible line, okay? We'll come back to that concept again and again this year. So slope is the constant rate of change between the points. Think rise over run, right? There are four kinds of slope, and let's fill those in. So one of them would be, and this is, I mean, that's kind of a weird statement, four types of slope. Well, there are four ways we could choose to categorize slope. Let's say it that way. So we could have a positive slope. What does that mean in terms of a picture? Like if I were to graph a line with positive slope, what's the defining characteristic of a line with positive slope? What's that going to look like? Okay, I see people holding their hands up. Right. So moving from left to right, the slope would be upwards, wouldn't it? It's an increasing slope, right? So an ant is always walking on a line with positive slope. The ant is walking uphill from left to right. So here would be just an example of a representative line. Okay, what about negative slope? From left to right, what's the ant doing this time? Walking what? You know, that'd be downhill, wouldn't it? So something like that. Okay. What are the other two? I mean, what are the other two possibilities? Either it's positive or it's negative. Well, what's between positive and negative numbers? 0. Okay, good. So we have a 0 slope. And you guys have already drawn the picture with your hands. A 0 slope looks like a horizontal line. And then what about the other possibility? What's the other possibility? Okay, vertical lines. And what kind of slope is that? What do we call that? Do you remember? Undefined. Yeah, we get undefined slope. And that would be a vertical line. Good. Okay, so let's do a couple things here. Let's write the equation in slope-intercept form and then graph the line. Okay, and so this is, you know, I know this is just major review for you guys, but I do want to just focus on one idea. Whenever we graph lines, the strategy is always going to be the same. When we graph lines, we're always going to start with an anchor point, so a point that we know, and then we will use slope to create another point typically, right? So the technique is always going to be, we're going to create 2 points and then connect and extend, right? And you're familiar with that. That's our goal. 2 points defines a line. That's all we need. So if we can create any convenient 2 points, we can always just connect and extend to graph the line or sketch the line. Okay, so what about one like this? Now they want us to put this into slope-intercept form. So what are the steps to put this into y equals mx plus b form here? Let's see, Pagan, what do I have to do first?
Are we on 9 or 10?
Number 9.
Okay.
Right
We need to switch the y. Oh no, y equals. We need to put the y on the other side, so we need to subtract 3y.
Okay, we could. Let's go ahead and leave the y on. I mean, that's optional. Let's leave the.
Then we could subtract y.
Subtract.
Or x.
X. There you go. Good. So subtract x. Okay, which gives us that. Good job. And then divide by 3. Good. So we divide everything by 3. Now, dividing by 3 is the very same thing as multiplying by 1/3, isn't it? Right? So we could also think about that as just distributing a 1/3 through both sides, which is going to give us a negative 1/3 x minus 5, right? And so there's our answer. There's our linear equation written in slope-intercept form. So what is the slope then? We can identify the slope by inspection, just by inspecting the equation. Olivia, what's the slope here? Negative 1/3. And what's the y-intercept? Negative 5. Good. Okay, and so then when we want to graph this thing, all we've got to do is we're just going to start at what point? Is there a point that we know? What's the point that we know here, Natalie?
Oh, for number 9 or 10?
Number 9. So what's our starting point? There's one point that we already know on this line. What's that?
Would it be negative 15?
Not negative 15. Look at the information. This is the important information, right? We found the slope and the y-intercept.
Negative 5.
Yeah, okay, good. The negative 5. And what we really mean, if we think about that as a point, what's the x-coordinate of the y-intercept always going to be? 0, good. So that's the point 0, negative 5, isn't it? So there's our anchor point that we can start with, right? So there's that point, 0, negative 5, right there. And then we'll just use our slope, right? We'll make a slope triangle. So our slope triangle is telling us we're going to rise. By the way, if a slope is negative, it's always convenient to think about the negative as being part of the numerator, right? The top. So it's part of the rise. You're either going to rise positively upward or negatively downward. So we're going to rise by negative 1, and we're going to run by positive 3, and that gets us to a second point. And then all we have to do from there is just connect and extend, and we get our line, right? Okay, what about then number 10? We got to get that into slope-intercept form. So, Maria, what do I have to do to get that into slope-intercept form?
I think for this one we can move the y.
We could move the y, but the y is already positive over here, so let's move the other stuff. But you could do it either way.
So then it'd be y equals negative 4x plus 1.
There you go. Good. So we're going to subtract 4x and add 1 to both sides. And so we get equals negative 4x plus 1. So then what's our slope? What's our y-intercept here?
1.
It's at 1, isn't it? So we go 0, 1. So there's a point, and our slope is what?
Negative 4.
Okay, so how am I going to give me a roadmap here? Where do I go from this point to get to another point so I can connect and extend?
So the rise would be negative 4.
Okay.
And then over 1.
Good. So I'm going to drop by 4, run by 1. I get a second point there, and then all I've got to do is connect and extend. You guys got this. Okay, no big deal. All right, so let's focus on on horizontal and vertical lines. Let's look at the equations of those. And we've already talked about this a little bit. Let's look at one like this. I'm going to make this red so we can see it better. So we've got this vertical line. We want to come up with the equation of that line. Well, what's that going to look like? What's the equation look like? Do you remember that stuff, Mackenzie? Do you remember what the equation of that vertical line is going to look like?
Would you just put y equals negative 3?
Y equals negative 3?
Or would it be x?
Yeah, it'd be x. Okay, now let's think why that is. Okay, look at all the points on this line. If we make a bunch of representative points, there are an infinite number of points, but let's just pick a few representative ones. Let's look at the ordered pairs. This ordered pair right here, wouldn't that be negative 3, positive 3? This one right here would be negative 3, positive 1. This one right here would be negative 3, negative 3, right? Well, what's in common there with all those points? What do they all have in common? Yeah, the same x value, right? Now think what a linear equation really does, right? If we go back and let's just pick one of these from the other page that we've been working on. Like we'll take this one right here. What does this do? This equation just gives us a recipe for connecting x and y values, doesn't it? Right? If I put in a certain x value, I can calculate the corresponding y value. Agreed? For example, if I put in something like x equals 1, let's just try that, right? If I let x equal 1, then what do I end up with? Let x equal 1. So we get y equals negative 4 times 1 plus 1. So I get y equals negative 3, right? If I take those together, I get the ordered pair 1, negative 3, which is right there, isn't it? I could do that with any conceivable x value. I could pick x equals, a billion, plug it into that equation, and I can find the corresponding y value. That's all the equation does, is it connects the x and y values in a predictable way. There's a pattern there that it gives us, right? Okay, well, look at this example here. This example here, it doesn't matter what the y value is, does it? The x value is always negative 3. It doesn't depend on the y value at all. We don't need to have some fancy equation because we know that the x value is the same all the time. So what's our equation then? X equals negative 3. That's it. That's the equation, right? Because we don't need to, y could be anything. There's an infinite number of y values in the infinite number of points on this line, but every single one of them has an x value of negative 3. So all we have to specify here is that the x values are always negative 3, and the y values could be anything. Okay? Does that make sense? Does it make more important, rather than just remembering, because you'll forget, just remembering that vertical lines are named as x equals a number, knowing why, you'll never forget it then, right? If you can think about the concept. Then the same thing would be true for a horizontal line. If we have a horizontal line here, well, what's going to be true for every point on that horizontal line? What's always true there? I won't even plot them, but they all have something in common. Liliana, what would be true of all those points? Yeah, y would always equal 1, wouldn't it? No matter how many points I drew, y would always equal 1, and it wouldn't matter what x is. It's the y value, we'd say in math, is insensitive to the x value. It doesn't make any difference what x is. So that's how we name that line, because the y values are always the same. Okay? Parallel versus perpendicular. So see what you remember about this. The slopes of parallel lines are what? What are those? Liliana, what are the, if I have two parallel lines, what can you tell me about their slopes?
If they're parallel?
If they're parallel, yeah. I didn't hear that. Say it again. Well, they could, if they're parallel, they could. Like, look, I could have, we graphed, let's go back to the previous page. So I graphed this line right here, this purple line, or how about this green line that had a slope of negative 1/3 and a y-intercept of negative 5. If I were to graph a parallel line up here somewhere, what could you tell me about their slopes? They'd be the same, wouldn't they? Good. Okay, so parallel lines always have equal slopes. Okay, and that's a pretty easy one to remember, right? Because obviously the ants have to rise and run by the same amount if their lines are going to stay the same distance apart. Carrie, can you remember what the relationship is between perpendicular lines? If two lines are perpendicular, so they meet at right angles, do you remember what happens there? They have to intersect, you're right, but what about their slopes? What's the relationship between the slopes of those two lines? They're opposites, that's part of it. So they're opposite, but they're not just opposites. Like I'll prove it to you. If I did something like the line, if I did the line with a slope of 10 that goes through the origin, that's a really steep line, right? If I did the line with a slope of negative 10, it's a really steep line with a negative slope. Those obviously aren't perpendicular, right? There's got to be something else there. They're opposites, but there's something else going on. Does anybody remember? Reciprocals. There we go. Good. Okay. So they're opposite reciprocals. Okay, I want to show you something, kind of an interesting relationship there. Did I make a page for it? Maybe I didn't. I'll just do it on here. Opposite reciprocals. Let's prove a little relationship here. This is a good one. So if I've got, let's say I've got two slopes. One slope, we'll call it M1, is equal to A over B. So if M2 is perpendicular to that, what would its slope need to be? A and B are just numbers. And B can't be, B can't be 0 in this case, right? We can't divide by 0. But as long as B is not 0, this tells us a slope. What would the perpendicular slope be? What do you think? Kendall? If M1 is A over B and M2 is perpendicular, what would its slope have to be?
Negative B over A.
Okay, good. Look what happens when we multiply these slopes. M1 times M2. I get A over B times negative B over A. Well, look. We get cross-canceling, and we get -1. Okay, so there's a really important relationship, and that's an easy way to check perpendicularity, right? If you have two slopes, their product, if they're perpendicular, the product of the slopes would always have to be -1. Okay, just a nice little thing just a little nugget to add there. That's a good relationship to see. Okay. Okay, so determine whether the pair of lines are parallel, perpendicular, or neither. Well, let's look at these and find out. Now, if I'm asked to determine if the lines are parallel, perpendicular, or neither, I don't need to overdo the problem here. What's the only thing I need to know about those lines to determine if they're parallel, perpendicular, or neither? What's the only thing, Jace, I've got to know about in problem 13 about the two lines? So I'm comparing these two lines here. Let's make this one, this will be the blue line. And this will be the red line. Okay. What's the only thing I need to know about those two lines if I want to determine if they are parallel, perpendicular, or neither?
So you need to find the slope of both of them.
That's it. Good. Right. That's all I need is the slope, isn't it? I don't have to graph them. I don't need to know y-intercepts. I don't need to know anything else. I just need to know slopes, right? So think about the process here that we're going to go through. This is kind of an honors level approach to this, right? So if I'm going to, how would I find the slope of the blue line? What would the steps be? Go ahead, Jace. What would you do to get the slope of that line?
So you would subtract 10x.
Okay, good. So I'd end up with 5y equals -10x plus 5. And then what?
And then you divide by 5.
And then I divide everything by 5. Good. Okay. Right. And I end up with y equals -10/5 is -2x plus, who cares? Right? I don't care about the other part. All I care about is the slope. So you could have really done that in your head, couldn't you? I mean, you see what I'm saying? Everybody see my point here? If I know that all I want to do is find out what's the coefficient of x going to be when I isolate y, I can do those steps in my head. If I want to get the y by itself, I can already see I'm just going to subtract the 10x and divide by 5. I'm going to get -10 divided by 5 is -2. You see my point? These are things that you can do internally without having to do a lot of extra work. So let's practice that on this guy over here. If I want to get the y by itself, just leave it where it is, right? And I need to know what's the coefficient of x going to be on the other side. Well, what is the slope going to be for the red line then? I'm going to get y equals what times x? If I isolate that y, what's the coefficient of x going to be? What are you going to get, Duluth?
You're going to get 1/2 x.
I'm going to get, okay, positive. You got to be careful about the sign, positive or negative. See, there's a negative there.
Oh, it would be negative.
Negative 1/2, wouldn't it? Right? Okay, so that's all I care about, right? Is that I got -2 and -1/2 for my slopes. I don't care about the other stuff. Once again, there's plus, who cares? Some other stuff. We don't care about that. So you tell me then, based on those two slopes, -2 and -1/2, are they parallel? Well, obviously not, right? Because those aren't equal. Are they perpendicular? Delube, are they perpendicular? There you go. Good, because they're not opposites. Perfect. Okay, so that answer would be neither. Okay, let's try, what about, let's just do this one real quick. So I want to know, here's my blue line. Just by inspection, do this in your head. What's my blue slope going to be, Dawson? If I solve for y, what's the coefficient of x going to be? If I solve for y? Oh, okay. Oh, you were looking at this guy, weren't you? Yeah. Okay. And you can just, and this is good practice. And this might seem strange for a math teacher to tell you to not show work, but I'm really interested in, as a teacher and just kind of as a student myself, I'm interested in brain science. I'm interested in the way that the brain works. If you leverage your brain's preferred way of thinking and organizing information, you're going to become a better student. One thing that's been shown to be true is that when you do mental math, you engage the same parts of your cerebral cortex that you do when you do algebra. So doing mental math is actually a way to just inherently strengthen your brain in its ability to do algebra. Okay, so this is a good thing. So I want you guys to kind of practice this a little bit. If I get that y by itself, I could either add the 6y. I don't care about the 42 at all, right? Not important. All I care about is the relationship between those two terms. I could either add the 6y to this side and divide by 6, or I could subtract the 8x to this side and divide by -6. Either way, what am I going to get there, Dawson? 4/3. That's it. Exactly. I'm going to get 8/6, which reduces to 4/3. Okay. How about over here? If I do the same thing over here, Chloe, what am I going to get? if I isolate the y, I don't care about all I care about is the coefficient of x. Okay, all I care about though is if I solve this, I get y equals what times x? 4/3. Yeah, there you go. So what's that tell you about these two lines? They're parallel. Okay. And then if we look at something like, let's see, how about this guy down here? Okay. If I were to, this is my blue line, how about? This is my red line. Okay, if I isolate the y up here, what's the blue slope going to be, Andrew Saxton? I don't care about that, do I?
Oh, for that one?
Yep.
Change that. Should be what? 3/2?
Yep. There you go. So I get, not y, I get slope, don't I? So that's my blue slope is 3/2. What's my red slope going to be, Andrew Deminu?
-2/3.
Okay. So what's that tell you? Good, they're perpendicular. All right, good stuff. Okay, give me a 1 to 5 real quick. How are we doing on this? Either click your cameras on or type it in chat. So far, so good? Okay, all right. So X and Y intercepts. All right, this is another thing that I know you've done all this stuff, but I want to pull it together more theoretically and conceptually than just the nuts and bolts of finding X intercepts and Y intercepts. Keep in mind that if we want to graph a line, all we need are 2 points and then I can connect and extend. We always want to pick the most convenient points, right? Well, oftentimes those are going to be intercepts, okay? So we know that the x-intercept is just where the point where our line crosses the x-axis. Y-intercept is where it crosses the y-axis. And so if we look like at this graph right here, the x-intercept, you guys all know this stuff, right? The x-intercept is going to be right there. That's where it crosses the x-axis. And the y-intercept is right there, okay? The x-intercepts are topics in algebra that we focus on a great deal. We can refer, and oftentimes we'll even have different names for them, right? Like we can refer to x-intercepts in a variety of ways. They could be, a lot of times when we're looking for x-intercepts, depending on the context, we might call it a root. We might call it a zero, or we might even call it a solution, depending on the context. And we'll talk about each one of those in detail throughout the year as we go through problems and we kind of, the context shifts a little bit. It might be more appropriate to talk about a zero than a solution in some cases, right? Okay. So how do we find x-intercepts and y-intercepts? Well, let's look at these coordinates real quick. The coordinates of this x-intercept are -3, 0. Right? The coordinates of this y-intercept are 0, +4. And obviously those zeros in there are not accidents, right? The zeros are there for a reason. We know that an x-intercept has to occur where the y-coordinate is 0 or it wouldn't be on the x-axis. And conversely, a y-intercept has to occur where x is 0 or it wouldn't be on the y-axis, right? So we can use that as a strategy. If we want to find the x-intercept, all we have to do is set y equal to 0 and solve for x, right? If I want to find the y-intercept, we know that's where x equals 0, so we set x equal to 0 and solve for y, okay? And then we can use those points frequently to graph an equation, right? So let's take a quick example here. Like if we wanted to do this one, if we wanted to find the x and y intercepts of this equation right here, well, what are we going to do? I mean, to find the x-intercept, what do we do? To find the x-intercept, we set what? Y equal to 0. And this is called the cover-up method for doing this. This is really slick. So if we have our equation here, y equals, now normally in class I just use my hand, but that's not going to work here. So I've got to make something to cover something up. So I'm going to, give me just a second here. Okay, so if I want to find the x-intercept, oops. I already know that is where y is equal to 0, right? So all I got to do is I'm just going to cover up the y. Oh, why is it doing that? Hang on here. I'll do that instead. I'm just going to cover up the y and solve for x, and I can do it in my head, right? You see the trick there? By setting that equal to 0, it just goes away. I can just accomplish that by covering it up and isolating x. Pretty slick, right? So you can do that in your head. What do I get if I solve for x there? What am I going to get, Adelaide? Yeah. So if we're using this cover up trick, right? If we want to find the y-intercept, we're setting x equal to 0. So you can just cover it up with your hand or with your finger if it's on paper, or in your mind, just cover it up and make it a 0. And then I'm just solving for x. So if I isolate, what would I get if I isolate the x? If that becomes a 0, so I'm covering it up. You could either add the negative, you could add 2x to both sides and divide by 2, or you could subtract 5 and divide by -2. Either way, what are you getting for your answer? Go ahead, Adelaide. I'll leave that one to you. 5/2, exactly. You're going to get 5/2, aren't you? Whoops, gosh, keep doing that. So 5/2. So that would be my x-intercept. If I want to find my y-intercept, well, then I'm going to set, I already know immediately that the y-intercept occurs where x is 0. So now I could take this and instead I'm going to cover up my x term, right? Because if x is 0, that whole term goes away, right? Okay, well, that's pretty easy to solve. What's y equal to? What's y equal to there? Anybody? Just 5. Okay, I see what people saying. Yeah, right there it is. Y equals 5. And we even knew that, right? Because this is, after all, slope-intercept form. So we recognize 5 is the y-intercept, right? But that technique's going to work always. Let's try. Okay. Well, let's just do this top one. Okay, let's use our little trick. And let's come up with the x and y intercepts. So the x-intercept is where y is 0. The y-intercept is where x is 0. Let's find the x-intercept. So I'm setting y equal to 0. And what do I get if I do that? Alan. Actually, Alan's just sitting down. I'll come back to you. Abby. Would be 1/5, exactly. Okay, if I want to find the y-intercept, I'm going to set my x term equal to 0, and that's pretty obvious then. It's already solved. Y equals -1, right? So if I want to graph this thing, I could go, and I'll tell you what let's do. Let's go by, instead of going by ones, because that's going to be really tiny, let's go by 1/5 on our graph. So this is going to be 1, 2, 3, 4, 5. So that's 1. This is 1, 2, 3, 4, 5. That's 1. You get my point? This is 1, 2, 3, 4, 5. That's -1. 1, 2, 3, 4, 5. That's -1. So we get a point at 1/5, 0. So I get a point there. And I get a point at 0, -1, which is right there. And I just connect and extend, right? And that's my equation. Okay? Make sense? Did we have to do it that way? No, we didn't have to do it that way at all on this one. That probably wasn't the smartest way. The smartest way would have just been to start at -1 and make a slope triangle, probably, right? But I just want to make the point that we can use these intercepts, and sometimes it's really handy. When it's really handy is actually not when you have equations that are in slope-intercept form. Let me make a different one for you. Like right here. Here's a good one. When it's in standard form. This is when that cover-up method and finding the intercepts is really handy. Okay. So like up here, we wouldn't need to, because look, we've got a point at 16/3 and we have a slope. We make a slope triangle. But here we do need to. What are our options? Well, we could put this into slope-intercept form and use the y-intercept and the slope, but we could just as easily not avoid that whole process and find the intercepts. Okay, so if I said x equal to 0, cover that up in your mind. If I said x equal to 0, what's y equal to? Solve. Ellen, what do you get? If I said x equal to 0, here, I'll cover it up. If I said x equal to 0, what's y? Solve for y there.
I don't know. I'm sorry.
Well, okay, so if I solve for y, I think you maybe stood up right when I was explaining this. So let me go through this real quickly, right? If we need 2 points to graph a line, so we could just choose the intercepts. When we're starting with a line that's in standard form, this is a really easy way to do it, okay? So if I set x equal to 0, I'm finding the y-intercept because the y-intercept occurs where x is 0. So that means that 4 times 0 is just 0. So I'm going to cover that term up. It goes away. I'm left with an equation only involving y, so isolate the y. What's the one thing I got to do?
Get the negative.
Yeah. Divide or multiply by -1, and so I get -8, don't I? Right?
Mm-hmm.
Okay, let's find the x-intercept. So that's where I'm going to set y equal to 0, so I cover that term up. Solve for x.
2.
Whoops, darn it. Right. And we're good. Right now I've got 2 points, so I can graph the point at 2, 0, which is right there. I can graph the point at 0, -8, which is right there. Connect and extend, and there's my line. Okay? You see where that comes in handy with standard form? Okay. How we doing? Give me 1 to 5. Type it in or show me hands. Okay. Okay. Oh, we're out of time. All right. So I'm going to put up some review assignments for you. We'll wrap up this linear stuff next time. These are be quick assignments. I mean, I just want to do a variety of problems where you get some practice kind of reminding yourself about how to deal with lines, but no big deal. Drop in after school if you need to get questions answered, do a retake, any or all of the above. Okay. Have a great day. I will see you on Friday if I don't see you sooner.